actually my circuit would look like this. So I will have one inductor and then it should be connected to a transistor, that is my T, and then you had a diode and then should be connected to a capacitor, and again it is connected to a load. That's my, this is R, right? C, this is my D1, this is my T1, this is L. So the across the voltage is VL and the current going through the inductor is my I, right? So what we did here, actually we just swap the load terminal and the source terminal, right? What was my load terminal for the buck converter? I just placed that terminal with the in the last class we discussed that, right? We just swap the condition. So for the buck converter, if we just replace the load and the source position, it will become a boost converter, right? So that's what we did here. Just give me 1 minute.
রেকর্ডিং শুনছি মানে কালকের ক্লাসেরটা শুনছি অনেক ক্লিয়ার শোনা গেছে না আমি তোকে নোটস দিব কি
Okay. So in that portion, so if I try to draw the waveform, if we have already drawn the waveform, right? So I just try to recap it for 5 minutes. So if this is my T and this is my BPE, so I am considering that. So I will put pulses across the switches T1 up to this time. This is my D multiplied by TS, and the time here is 1 minus D multiplied by TS. Again from this portion I am giving pulse to VBE, so meaning that whenever I am giving pulses to this transistor between base to emitter, the transistor will turn on in the saturation mode, right? We discussed that, right? So whenever we are operating a transistor, either we will operate in the saturation mode or the cutoff mode, right? Okay, so now I want to draw the waveform based on this condition. So what is happening here? During mode 1, what will happen? This transistor will turn on, right? So this transistor, actually this transistor, it will turn on, right? So if this transistor is turned on, so this transistor will turn on, right? So if this transistor is turned on, what will happen? The circuit will look like this. Then there will be a diode here. It is connected to the capacitor, and then again it is connected to the load. This is my plus minus V naught. Since this diode is connected, anode of this diode is connected to the ground and cathode is connected to the positive terminal voltage V0. So as you can see, your anode voltage is getting lesser than the cathode voltage, right? So meaning that this diode, it will turn off, it will behave like a open circuit form. Yeah, sure. As I said, what is the condition for the diode to operate? I always remember this like this, A here. This is only couple. So your anode voltage should be greater than cathode voltage, right? So whenever, suppose this is my anode terminal and this is the cathode terminal. So the anode terminal is connected to the ground, right? But your cathode terminal is connected to the positive voltage sign, right? Meaning that your anode voltage is lesser than the cathode voltage, meaning the diode is operating in the reverse bias mode, right? Make sense? No? So now, if this is happening, then what will happen? The inductor voltage and the current through the inductor, if I do Kirchhoff's voltage law, we will get that your inductor voltage, it would be equals to your source voltage, right? So your inductor voltage is nothing but L multiplied by del IL1 over T multiplied by Ts, right? We know how we get this condition, right? It should be multiplied by Ds. That gives you del IL1, which should be equals to Ds over L multiplied by D multiplied by Ts, right? That should be your inductor current equation, right? And if I consider this is my inductor current and this is my load current, if I apply KCL here, it meaning that my IC plus I naught, it gives you 0, right? Meaning that your IC would be minus negative of I naught or the load value, right? And that should be equals to minus V naught over R, right? Right? What is the voltage across the resistor? V naught, right? And if you divide the voltage with the resistance value, you will get the current, right? Make sense? So, during the positive half cycle, so up to this portion, if I try to draw the inductor voltage, this inductor voltage will be equal to the source voltage, right? That will be equals to Vs, right? Any question? Any question? Okay. For mode 2, so if I try to mode 2, go to mode 2, what will happen here? So in mode 2, there will be no voltage between base to emitter, right? Meaning that this transistor will turn off, right? So if this transistor is turned off, you have an inductor and then this transistor is turned off. Any question? Any question?
So the direction of the current of analysis. So in this case, the transistor is in saturation regime. So the diode here is open. Is the capacitor discharging here?
Should it? Actually, it will be dependent on the RC constant value. Okay, because the charging and discharging through the capacitor, it depends on the RC value, right? That is the time constant, right? So what is happening here is that during this time is very large or very small? Very small, right? And this capacitor value is too high that actually the current almost remain constant with very small ripple. Okay, so the voltage here it will be a constant one with a minimum percentage of ripple. It should be less than 0.5% or 1% in this way, because the capacitor value is too large that it will take much more time as compared to this switching cycle to discharge fully. Make sense? Okay, so now if the diode is like this and then we have load, so the inductor current now it will force the diode to turn on, because it needs a path to come back to the source, right? And we said that in the last class also, inductor doesn't like the current to change, right? So they will force this diode to turn on, and then if this diode is turned on, then we can simply replace this diode, because we are considering a idealistic case, right? So we can consider this diode to be a short circuit one. Okay. So now what should be the voltage across the inductor?
Vs minus.
So this is my V naught. This is Vs. So the voltage across the inductor it should be. So we can write L multiplied by del I L2 over 1 minus D multiplied by Ts, right? That is the time. It should be equals to Vs minus V naught, right? So that should give you del IL2, that should be equals to Vs minus V naught over L multiplied by 1 minus D multiplied by Cs. That is your equation number 2, right? And if I now put a KCL at this node, so the incoming current is your IL, right? Right? So, and if this is my IC and this is my I naught, so we can write your IL is equals to IC minus plus I naught, right? So your IC it should be equals to IL minus I naught, difference between these two, right? Okay, so now during this time we had made some of the assumption. What was that? That switching time period V of lambda d lambda that should be equals to 0, right? So the total voltage across the inductor within a complete switching time it should be equals to 0, right? But if you integrate this thing, this area, it will give you a positive number, right? So during the time, this time, you should have a value that is negative in nature. You should have a value that is negative in nature, so that the area here it becomes negative, right? So that for the total switching cycle, this area will cancel out this area to make this integration 0, right? So this value it should be your Vs minus V naught. What does it mean? It means your output voltage should be greater than your source voltage, right? Right? So similar way, for the next one cycle also we will get the similar waveform like this. So now if I want to draw the inductor current IL, what will happen here? So during, okay, before that one, if I want to implement this equation also, so what we can write, Vs multiplied by what is the time between these two? D multiplied by Ts, right? So Vs multiplied by D multiplied by Ts plus what is this value? Vs minus V naught multiplied by 1 minus D multiplied by Ts, that should give you 0, right? So from that one, if you try to solve for Vs and V naught, you will get your V naught would be 1 over 1 minus D multiplied by Vs. So if you put your duty cycle less than 1 but greater than 0, you will always find your V naught is greater than Vs. Okay. So this thing up to this point, as I remember, we did in the last class, right? So if your V naught is greater than Vs, then this thing, this magnitude, will that be positive one or negative one? Negative, right? So meaning that this will have a negative slope. But during the positive half, this magnitude, it is a positive thing, right? Because your voltage source is positive, inductance value is positive, so the ratio between two positive number will give you another positive number, right? So if I take this value to be my average value, so what will happen? During the positive half cycle, it will charge up like this. And during the negative half cycle, or when the switch is off, it will come back to 0, and then again it will charge up, and then it will discharge like this. So this point, it will be my IL max. This is my IL mean, and this value in between, that is my what? IL. IL means IL average, right? In the last class also we say whenever we are dealing with the capital letter, it means it's a average value. When we deal with the small letter, it means it's a time varying quantity, right?
So can you say that for boost converter we are stepping up voltage only in negative cycle?
Not necessarily. It's happening for the complete switching cycle. Actually, what is happening? What is happening here is that this inductor, it is storing energy, right? During when this switch is on, but no energy is being put to the load, right? Right? But whenever in the condition 2, this energy, the energy inductor has, also the battery, both are providing energy to the load, right? So that's why the load will have energy higher than the, not higher, it will boost up to some extent so that the voltage becomes higher. It makes sense? Because your energy is balancing, right? So you cannot have more energy than the input. But what is happening here, during when this switch is off, what is happening there? This inductor and this source effect, what they are doing, they are adding up the voltage so that this voltage becomes higher than the what? Source voltage.
So is it similar?
Is it?
Is it similar to clamper?
Yeah, you can say, but clamper it's a different thing. You can say like this. Yeah, it's a kind of clamper. During this portion, it's a kind of clamper circuit. But for clamper circuit, you need to have a capacitor, right?
Here the inductor is doing work.
Yeah, because it is storing energy in the positive half, and then it is pumping that energy to the load in the next half. Okay, so now if I want to draw the output voltage for load, so if I do I load, your I load should be what? So I load should be a constant value, right? Because your output is constant. So your output is constant and your resistance is constant, meaning that your output current, it should be constant as well, right? That should be your V naught over R, right? So now if I want to draw the capacitor current IC, so what should be my IC? Is it raining? Okay. That's very bad for me.
Wait for us also.
Why is that? Because I have to go back to this. Okay. So now, whenever during this d multiplied by ts time, actually what is happening? That in capacitor, it is actually, it should be equals to the negative value of the current going to the load, right? So during this time, this capacitor current should be negative. That should be V naught over R. So this initial value, it should be negative value, okay? But what is happening when mode 2 is on? Your capacitor value, it should be equals to what? Your inductor current plus output current, right? So meaning that here this value, this IL value is exactly same as V naught over R, right? Right? So actually this part of the inductor current, it will go through the what? Go through the capacitor. Why is that? Because this inductor current, we can consider the average current multiplied by this triangular current, right? So your inductor current, it should be what? Your IL plus, we can say IL triangular. This portion, right? This is your triangular current, right? Superimposed on a DC current, right? But your DC current is actually equal to your load current, right? Not like that, but whatever current, average current it is coming to the load, it is actually getting from the inductor current, right? So if I do this I naught, this thing and this thing, actually same thing, right? So the capacitor current will be nothing but the triangular current when this switch is off, right? So you will get the triangle of it, so your capacitor current will be like this. So that is the triangular portion of this current. Confusion about that? What I say is that suppose this value is 55 amps, this value is 50 amps, okay? So, and the load current, it is also 50 amps, right? So what should be your capacitor current here? 5, right? Right? And what should be the lowest current? What should be the lowest current? minus, no, actually what is happening here, you have to remember that your IC dt, that should also gives you 0, right? The voltage across the inductor, it should be 0, and the current through the capacitor, it should be also 0, right? So meaning that this area, it should be equals to this area, right? So that if you add up these two things, it will become 0, right? So this area, actually what is happening here is that your load current is constant, right? But whenever this value is higher than this thing, so actually if you kind of between this thing, it is not taking any current from the inductor, right? For this part, is it taking any current from the inductor? It is not taking any current from the inductor, right? But here, what is happening here is that whenever you have a change from this part to this part, okay, so this thing will be appearing across the capacitor current, so that this area actually becomes this thing, so that if you add them together, this total current becomes 0. Not clear?
So, but at the same time, we have to make IL is equals to IC plus I naught, right?
IL equals to,
IC plus I naught.
yeah, so IC equals to I naught, you should make that is right. So here, okay, let me write that again. Your IL is what? IC plus I naught, right? So this IL, this thing, it is below IL, right? This term, this portion, this is below IL, right? This term, this is above IL, right? Okay, okay, I know. So your IC, whatever change is happening in the IL, it should be covered by both IC and I naught, right? So what is happening here is that whenever up from this portion to this portion, IL doesn't have any effect on the output current, right? Or the capacitor current, right? So now when up to this portion from here to here, if your load current is changing, no, the load current is not changing, right? So now what is happening here is that here to there, these 2 points, your output voltage is higher, right? Sorry, inductor current is higher than the average current, right? So during this time, it should be positive but going downwards, right? Right? Okay, so when it goes below this one, then what will happen? Okay, so sorry, I just made one mistake. Sorry.
So can you use a different color for the?
Yeah, sure. I am doing that. Okay. So what is happening here is that so during the negative half cycle, it should be like this, right? Because your IC current is nothing but your output current, right? Okay. So now what is happening here? So your IL current is higher than the average current, right? So in that case, the difference between these two, it should be positive, right? So here it should be positive like this, and then when it starts to decay before that thing, it will become negative and blue like this. Because here up to this point, what is happening here? Inductor current is what? Less than the load current, right? So your capacitor current should be negative, right? So that this capacitor current is going in the opposite direction to make IL plus IC equals to your I naught. Make sense?
Why is the current line?
Because this is 55, suppose this is 50, so this curve should go like this, 5, 4, then here you can say it will be like this, because the difference between these two, it will be 0 here, right? And then it will go like this.
And the negative part also be a slope. Yes, sir. So negative চলে যাওয়ার পর slope থাকে না একটা পরের দিকে।
Why is that? We are just now, whenever we are talking about difference, we are talking about the magnitude difference, right? Right? So one more thing is that the average current here. Okay. Oh, sorry. One more thing. If I know the relationship between V0 and Vs, so what is happening here? Okay, let me just discuss this thing, why this is happening here. So suppose this is a DC to DC converter, and your input voltage is what? Vs, and input current that is going to the inductor current. Suppose this is my inductor current, IL. Because inductor current is the input current, right? That is connected to the source. So your IL is equals to IS, right? So your output thing, it is connected to the load. That is my R naught, right? And this is my current I naught. So now if you see the Vs, Is, it should be equals to, because whatever we have here in between, whatever we have here, up to this portion, do we consider anything that can consume power? It's a lossless thing, right? Meaning that your Vs, Is, it should be equals to your V0, I naught, right? So instead of Is, we can write it as IL, right? So your Vs, IL, that should be equals to your V0, I naught, right? So what should be your IL? IL should be V0, I naught over Vs, right? So what is your V0? So your IL, it should be V0. If I try to write V0, so it should be V0 I naught divided by what is your Vs? Vs is 1 minus D multiplied by V0, right? So here we write V0 minus 1 minus D. So if you simplify, this should be IL equals to I naught over 1 minus D, right? So in that case, what I said here, actually this IL, does it equals to your I naught? No. That's why we are not being able to solve that thing. So what is happening here, your average value of the IL, right, your average value of the IL should be higher than average value of the I naught. No, if your D value is less than 1, so you will find that your IL is always higher than I naught, right? It's a kind of DC to DC transformer, right? So if you step up the voltage at the output, your current will go down in the same number so that the power becomes same, right? So from here to here, your voltage is step up, right? Then what is happening here? Your current should be step down, right? So whatever we are saying here, actually, this I naught here, it should not be equal to IL average, right? It should be less than the IL average, right? So that's why what is happening here is that instead of having a negative slope here, we will get the waveform like this. You got my point? Sorry, I just made some mistakes in understanding, but you now understand what is happening here, right? Because your IL would always have a average value that will be less than the inductor volt current value, right? Any question? Sorry, I made some confusion. I am sorry about that. So again, then during that negative half cycle, when the transistor T is on, it will be like this, and during the switching time when diode will be on, it will have a value like this. So this will be the current waveform for the boost converter. So let me just crop these things, and then I will try to write it down in the next page. So now this is my waveform. কার্সরের সাইজ কি করব আর একটু বাড়াবো আচ্ছা এটা একটা সমস্যা কারণ হচ্ছে কার্সরের এটা বড় করা যায় না তাহলে একটা কাজ করি নেক্সট what I will do from the next class I will write it on the board, okay? Because here the cursor I cannot make it larger, I think. We can do that, but if I write it, you can understand it will be like me, very thinner line, right? How? Yeah, I'm very good at learning. They will ask permission for that. It's for the mouse, not for the pen. Yeah, whenever I'm using my mouse, it will do this. So So how much time will it take? As if this is raining, I can have 10 minutes more, right?
Yes, sir.
Because you have no place to go.
অটো দিয়ে
first 2-3 years when I was being appointed there as a lecturer. So I used to play whenever it rains, no matter when I am in my formal dress or I am in my casual dress. So after that class, I used to go to the field with the football and play with the little children that we have in the dormitories. So I used to play with them. It depends on where this is played. Okay, so now the confusion is gone, right? So we understood the concept between this one. So now from here we saw this IL is I naught over 1 minus D, right? So here we can write IL is equals to I naught over 1 minus D, right? But what is my I naught? It should be my V naught over R, right? And that should be multiplied by 1 minus D. What is the relationship between V naught and Vs? 1 minus 1 over 1 minus 1 by D multiplied by Vs divided by R into 1 minus D, right? So it should be equals to Vs over R multiplied by 1 minus D whole square, right? Right? You understood, right, where I got it from? So your IL would be nothing but
It's an invitation
Okay.
from the university for the class.
how much backup time can we have? Okay, so now this is my IL. So what should be my IL max then? Your IL max, it should be equals to your IL average plus del IL1 over 2, right? What was my del IL1? It should be Vs over L multiplied by D into Ts, right? You might ask, sir, why did you choose this value? Because in the buck converter, the inductor was connected to the load, right? So we wanted to have everything connected in relationship with the output voltage, right? But here the inductor is connected to the source, so we want to have everything that is connected to the source equation. Okay, so that's why we are considering this rising slope. Okay, so what should be my del IL over 2? It should be, if I put this value, it should be Vs over R multiplied by 1 minus D whole square. And what should be my this value? It should be plus half del IL was what? Vs over L E multiplied by Ts, right? How I can do that? I know what was the voltage across the inductor. That was Vs, right? Divided by L, and whatever was my time, it was E multiplied by Ts, right? So if I take Vs common, then what we will have? We will have 1 over R multiplied by 1 minus D whole square plus 1 over 2 LFS multiplied by D into multiplied by V, because I have already taken Vs common. Your Ts is nothing but 1 over Fs, right? So I just put Fs here on the bottom. So what should be my IL mean? IL minus del IL 1 over 2, right? So it would be similar, Vs multiplied by 1 over R multiplied by 1 minus D whole square plus 1 over twice L Fs multiplied by D. Sorry, it will be a negative sign. Okay. Then, like the previous case, we discussed what should be my L minimum value. What should be my L minimum value? Yeah, so that should be my IL mean. It should be at least 0, right? Not, it should not have value lower than that one, right? That should be the extreme point, right? So, if I draw it with the, so if my inductor current is like this, so that should be the critical condition, right? For the continuous current, and for that one we consider that this value IL mean it should start from 0 and it will come back 0 and then again it will start from 0, right? So using that one, we can write Vs multiplied by 1 over R 1 minus D whole square minus 1 over twice L Fs multiplied by D, that should be equals to 0, or we can write 1 over R 1 minus D whole square, that should be equals to 1 over twice L Fs multiplied by D. So here we are considering it L minimum. So finally we got the value for L minimum. It would be equals to, oh sorry, yeah, it should be okay. So now my D should be here. So we can write L mean it should be equals to R multiplied by D multiplied by 1 minus D whole square over what? Twice Fs, right? So that should be my L minimum value. We have to have a L minimum value such that we will make sure we will always put this L value greater than L minimum value to make sure that our inductor current operates in a continuous current mode. Make sense? Now, if I want to derive the equation for the capacitance value, what was the condition? What was my capacitance? We know C equals to Q over V, right? So meaning that we can also write it as del Q over del P, right? So we can write it as my del Q, it should be C multiplied by del P, right? C multiplied by del P, right? So here what is my Q? Q is what? IC multiplied by dt, right? So if I want to get my minus del Q, if I take the area of this thing, I can say this is my del Q, right? Because at steady state we also said that my IC dt it would be equals to 0, right? So meaning that whatever negative value I have here, this area should be exact equal of the negative value, so that whenever we are combining them, that adds up to 0, right? Right? So what is the area of this one? So if I consider the del Q magnitude, what should be the magnitude? So it should be length by width, right? So what is my length? V naught over R. And what is my width? E multiplied by TS, right? Or we can write V naught over R Fs multiplied by D, right? So this del Q is nothing but C multiplied by del V, right? It should be equals to V naught D over R multiplied by Fs. That gives you, so we can write that gives you del V naught over V naught. It should be equals to what? So from here we can write C is V naught D over R Fs del V naught, right? So what should be my del V naught over this thing? So del V naught over V naught, it would be equals to D over R Fs C. So if you want to make this ripple again small, what we need to do? You have to put a large capacitor so that this value becomes lower for the same voltage, right?
So higher del V naught means higher ripple.
Yeah. Del V naught means what?
Difference in voltage.
So you should have a ripple like this, right?
Yes, sir.
So for the same voltage, if you want to remove that ripple, what we need to do? You have to put higher capacitance value to avoid the ripple voltage, right?
This is a better filter.
Yeah. Actually, if you put a very big capacitor for the small period, it will actually work like a filter, because the time requirements tau, it is R multiplied by C, right? So if you make C higher, your time constant should be higher, right? So it means that its charging and discharging time will be very low as compared to the switching time, right? Meaning that the voltage will be very much constant. If you put it for a longer period of time without any switching, then it will discharge to its zero value, right? Make sense?
Decay is very slow.
Yeah. So this RC, for this pulse, if you have a waveform like this time, if it is very small as compared to the time constant, then what will happen? That capacitor will not have to have the time to discharge, right? Meaning that the capacitor voltage will be fixed for that time. But if you make this thing higher and higher and higher, then the capacitor will start discharging like this. Make sense? How much time we have?
So 30 minutes.
30 minutes, okay, let's do one man. That is good. I will get chance to enjoy the rain. Actually, I don't know. In order, as I am deriving everything, it takes more time to finish one topic. Okay, I am way much behind the schedule. So,
আমাদের তো দেখো
when I was an undergraduate student, my sir used to say that a teacher will be always the student will always object about your behavior. Even you teach them very less syllabus, After they get passed and when they will look for the job, they will say, this teacher, he didn't taught me anything. But if you taught them new syllabus, as you will teach him new syllabus, they will even object about that. But they will say good thing about you when they will look for the job. So either way, the student will always object because you do good. Let me finish. You do good based on your ability, right? But you do bad in the exam because of the teacher, right? Because the teacher didn't make the question to your expectation, right? So it's always teacher's fault. Just how much time we have? Just we will do the introductory thing and then the rest of the math we will do in the next class, okay? Okay, so that is my example 6.5 for the boost converter. Actually, this type of question I will twist it a little bit so that I want to make sure that you understand the thing properly.
What I say?
I will make things not easy as it is given in the book, okay? I will do some parameter so that if you understand it well, you will be able to answer that question. Otherwise, whatever you do, you will never get the exact solution.
Can you give us some samples? Give some samples.
What?
Will you give us some samples?
Surplus. Okay, so what they say is that suppose we have a boost converter and then we have a switch like this, then we have a diode, then we have a capacitor and we have a load, plus minus V0. This is my R. Okay, so this says that your output will be fixed at 8 volt and your current at the output is also fixed 1 amps. Okay, so you have a boost converter whose output voltage and current is fixed. Okay, but your input voltage Vs, it can be varied from 2.7 to 4.2 volt. So you have a boost converter whose input can be varied but output will always remain fixed. Okay, so now they first say calculate the switching frequency. And second, it says that design the circuit in such a way that total current change IL, del IL, it should be not more than 40% of the IL load. Whatever is the average value of the inductor, the total current change, it should not be more than 40% of that one. Okay. Similar way, it says the total voltage change across the capacitor, it should not be more than 2% of the output voltage. So you know the criteria, right? you know the criteria, right? So now what will happen? You need to design your LC in such a way that this thing will be accomplished, right? So first thing we need to know what should be my switching frequency. So here we have a freedom to choose any switching frequency, and if your switching frequency is different from whatever he is choosing, it's fine. But we have to make sure that the switching frequency is in the range of kilohertz, not in the range of megahertz. Why is that? If you turn the switch on and off too frequently, what will happen? There will be a huge switching loss. Switching loss means that is loss, right? So that cannot be provided to the load. But if you put the switching frequency very or the frequency very low, what will happen? The value of the inductor and capacitor would be very. The value of the inductor and capacitor would be, if you put the switching frequency low, then what will happen? The value of the inductor and capacitor, it will be very high, right? So if you put this low, the value of the inductor and capacitor should be very high, right? That is another cause why we need modulation with the signal. Whenever you transmit a signal, communication, right? You are very good at communication. So why do you use modulation in communication? That antenna size is one of the causes. Another cause is that whenever you receive the signal, you need to isolate the modulating signal and the message signal, right? So if your frequency is not high, then the inductor and capacitor that you need to use as a filter, their size will be very huge. The more you increase the frequency, the size of the filter circuit, it will be very small, right? So that's why you have a modular circuit with small compact packages right now, because of the increasing the switching frequency, right? So you have to make always a trade-off between the inductor capacitor size and the frequency. Okay? So that's why I say you always choose your switching frequency in range of kilohertz, not in megahertz. So in your book, for this example, they choose the switching frequency to be 200 kilohertz. Anyway, but we have to make sure that it will have the inductor and capacitor value that will not be very large. Suppose if you choose a frequency that gives you inductance value of 1 Henry, do you know how big the inductor is going to be? You always deal with the inductor that is in range of what? Microhenry or millihenry, right? So I did my research on energy storage, that is called supermagnetic energy storage. So that energy storage device that can have a value of 1 farad, 10 farad, 50 farad, 100 farad. So that will be the huge thing that need to be cooled down by a refrigerator. So you have to choose a frequency in such a way that the inductor and capacitor value gets lower, so that it can be designed within a small space. You got my point, right? Okay. So now then we have two extreme voltage, that is 2.7 volt and 4.2 volt, right? So we know for boost converter your V naught is what? 1 over 1 minus D multiplied by Vs, right? So if I want to solve for T, your D would be 1 minus Vs over V naught. That is your D equation, right? Right? So whenever your output voltage is fixed, right? But input is varying. So if your input is settled at 2.7 volt, then what should be my D? D mean, if I say D mean, so it should be 1 minus or it should be D max. So D max, it should be 1 minus 2.7 over 8. That gives you Zero point 6625 means 663, right? Okay. So now, if your output input voltage is 4.2 volt, what should be your D mean? 4.2 over 8. So that gives you 0.475. So one thing we have to make sure that whatever thing is used to give it a pulse, this should have a value. This should have a value in between what? 0.475 less than or equals to D less than or equals to 0.663 in this range, right? Because these are the two extreme points, right, that the booster circuit will be operated, right? So that should be the D range. So we will keep it as it is as of now, and from the next class we will discuss how you can choose your inductor and capacitor. Okay? Any question?